Hello everyone, we are Light Sleeping Dragon and Young Phoenix, representing the light side in the text-to-image output detection team. The problem we are tackling is increasingly relevant. Generative models such as Stable Diffusion, Midjourney, and DALL-E can produce photorealistic fake images that are almost indistinguishable from real photographs. These images can be used for misinformation, identity deception, or forged evidence. As a light side team, our goal is to defend digital authenticity. Specifically, we want to design a system that can automatically determine whether an image came from a real camera or was synthetically produced by a generative AI model. Our approach focuses on robust multi-detector fusion. Instead of trusting one single detection algorithm, we integrate several specialized detectors so that they can complement each other's weaknesses. The result is a unified, reliable pipeline that any researcher or organization can use to screen large volumes of content efficiently. Our technical foundation is SeedBench, an open source benchmark for synthetic image detection. SeedBench provides implementations for multiple existing detectors, each trained on different datasets and optimized for specific visual cues. We realized that every detector had a blind spot. Some rely on frequency domain analysis and are sensitive to compression. Others depend on semantic inconsistency between captions and visuals. Therefore, instead of picking one model, we created an ensemble that unifies 5 state-of-the-art detectors. These are DIMD, Rhine Defect, Patchcraft, which also known as RPTC, and CNN Detect. DIMD detects hidden diffusion artifacts left by the sampling process. Rhine focuses on residual frequency noise that differentiates synthetic from natural texture. Defect uses a combination of clip and bleed encoders to match text-image consistency and expose semantic contradictions. Patchgraph looks for unnatural patterns in local patches, often seen in diffusion-based images. CNN Detect analyzes pixel-level noise introduced by convolutional upsampling layers. Each of these detectors excels in some cases and fails in others. By combining them, we cover a broader range of manipulation type. The idea is that even if one detector is fooled, the others can still recognize suspicious artifacts, and our system can form a consensus decision. Conceptually, our ensemble works like a committee of experts. Each detector gives its opinion, and our final verdict is based on the majority vote and average confidence. Let's look at how the system is designed. We implemented our workflow in a Python script named testmulti5py, integrated within a Google Colab notebook. The Colab version makes it simple for any user to reproduce the results because the environment setup, model downloads, and execution are all automated. The panel performs 4 main stages. The first one is the environment initialization, installing dependencies such as PyTorch to walk to transformers and OpenAI Clip. And the second one is the model loading. It automatically fetching pre-trained weights for all 5 detectors into a unified directory. And the third is the batch inference, which running each detector sequentially on the same set of test images. And the last will be the result merging section. It combines the individual CSV outputs into one master field called results combined CSV. The final CSV contains every detector's predictor probability and label, followed by 2 ensemble fields, average score and vote label. The system can be executed with only one line of code, which is the Python test multi5.py data path content images out directory to the content sidebench multi-out. Once it executed, it automatically processes all images and generates a clear, easy-to-read output table. This design ensures that other light or dark teams can reuse our tool instantly without retraining any models. Now I will pass the mic to Xiaojun.
Okay, now we will demonstrate the pipeline in action. In the Collab interface, we first up the images to this folder. We can upload these pictures, and after that we can run these functions, and the system recognize and file type supported by the detectors such as JPEG and PNG. After executing the command, the notebook begins running each model one after another. DIMD ran and the CN detector run relatively fast, while deepfake takes longer because it performs both images encoding and caption generation through BLIP. As the process finishes, the CSV file are produced. The CSV file merged function consolidation them by image frames. In the merged result combine the CSV file. You can see over here, and each image is accompanied by 5 prediction scores, 5 bandwidth labels, and average score and vote label. The average score represents the meaning probability of being AI generated, and the vote label becomes 1 if at least 3 of the 5 detectors classify it as fake. The entire workflow is reproducible on any club runtime. We purposely engage the dependencies so that they remain compatible with Python 3.12 and the latest CU and toolkits. This allows other teams to plug in their own images or transformations and immediately evaluate robustness against our ensemble detectors.
Okay, now the result is out. Let's analyze what we obtained. So we can see here we have input 8 images here. So the table here show examples output of all 8 test images, but now we just analyze one real images and one fake one. So we can see the fake one.png is an AI generated picture which created with stable diffusion. So DIMD gives it a probability of 0.000133 being fake, and the rhyme gives a probability of 0.72, deepfake give 0.99, patchcraft give 0.934, and CNN detect give 3.56. And the average score of this image is 0.52 and gets a word label of 1. So the example average was 0.53, which currently suggested suspicion even though one of the detector have failed. And looking at the real one.jpg, the DI is a genuine photograph received extremely low probabilities from all models, resulting in an example score near can you scroll to the right? We can see the average score of the real one.jpg is 0.2629. It has an example score near 0, and therefore it gets a word label of 0, showing that it's a genuine photograph. These examples highlight 2 important findings. First, diversity helps robustness. Models that rely on different features make different mistakes, and the example mitigates those errors. Second, the work mechanism provides transparency. We can see which detectors agree or disagree and study why. We also ran small scale qualitative tests. So across these 8 mixed images, individual model accuracies range between 78% to 89%, but the example reached about 92%. False positive dropped by roughly 20%, meaning fewer real images were misclassified as fake. During analysis, we noticed that clip-based detectors such as deepfake and rhyme excel at catching text-to-image inconsistency, while CNN detect struggles with highly compressed JPEGs. This insight will guide our future weighting strategy. In short, the example achieved both higher accuracy and more stability compared with any single model.
Interaction with other teams was an essential part of this assignment. We invited several dark side teams to test their generated or modified images on our detector. Some tried blurring down spamming or injecting random noise to evade detection.
The interesting outcome was that even when one or two detectors were full, others still triggered an alarm. For instance, patchcraft and deepfake often compensated when CNN detect fail. This cross-validation across models is exactly what we hope to achieve. Looking ahead, we plan to introduce weighted voting, where stronger detectors like deepfake and rank contribute more influence to the final decision. We also want to perform fine-tuning using adversarial examples to improve resilience.
On the ethics side, we consider the responsible declaration of pipeline as a defense tool rather than as a general purpose detector that could be measured. We also discussed adding a confidence threshold feature so end user can adjust the strictness depending on context.
Overall, collaboration and ethical reflection have been just as valuable as the technical work itself. To conclude, we successfully built a fully functional, reproducible multi-detector example that can identify AI-generated images more reliably than any standalone model. The system integrates 5 state-of-the-art detectors under one unified collab workflow, producing consistent results and detailed output files for transparent evaluation. This project
This project demonstrates how light-side research can proactively countermeasure the user-generated AI and promote trust in digital media. We believe our multiple model function concept could be extended to other modalities such as text to video or voice synthesis detection in the future. Thank you very much for watching our presentation. We are Light, Sleeping Dragon and Young Phoenix.